All right, our third speaker is Philip Schmitz, who is going to talk about SecureView. Philip, I'll let you take it from here.
Thanks. All right, then welcome to my talk about SecureView. It's about visualizing defense against transient execution side channels. It has been conducted as a byproduct of the research on our own security architecture, together with my colleagues of RPTU Kaiserslautern, University of Lübeck, and Stanford University. But yeah, first let me take you back to 2018, when the transient execution side channels made the news all over the world. It was a big, scary thing, and yeah, it affected the security of most industrial processes. But how do these attacks work? The transient execution side channels, or short TESS attacks, they exploit the side effects of instructions that are executed speculatively or out of order, and later discarded due to misspeculation or an exception. But even though the architectural state is reverted after the misspeculation, the instructions leave a microarchitectural footprint that can be used to reveal confidential data. May sound complicated at first, but let me run you through a quick example. This is one of the first attacks, the classical Spectre version 1 or PhD. We have an if condition that checks if our index is within the bounds of our array, and then we do a load from the index and do something else after, and we run this within a loop. And then our branch predictor always says, okay, we will take this if condition. And if we can, as an attacker, can choose the index X, we can have an offset that points to some different memory location that could be a secret in the memory. And then later we also need to transmit this secret data by, for example, accessing a primed array, and then it can be reconstructed by a victim probe or any of these cache-based side channels. And yeah, the discovery of Spectre and Meltdown kicked off a big field of research. I mean, the first presentation today was also from a person doing research in Spectre attacks. And yeah, it can be done either in software by adding speculation barriers to the kernel, or doing it more sophisticated. But we've also seen from the example of speculative load hardening versus STT that hardware might also be a good idea. And this can be done by closing high bandwidth channels, so for example the cache, or by selectively delaying some instructions under some conditions. But prototyping hardware is a costly process, so we need something else, and this is where researchers mostly go to Gen 5 for, because of its flexibility, its inside and debug capabilities, and yeah, it gives a performance estimate. And I did a quick backward search on Google Scholar, and this is out of all papers citing the first Spectre paper, and then searching for Gen 5 in there, and we have 331 hits. But yeah, we want to know if our architecture is really secure. And yeah, my background is that I'm coming from a group that works on RTL and uses formal verification most of the time. But in Gen 5, it's not as easy. So what's often done is pen and paper proofs, so arguing. And there has been some work on automated design time testing on this year's US+. And what's also often done is launching sample attacks, and they either succeed or fail. But yeah, you don't know how the attack is really mitigated, or if it was a coincidence or not. And then what also exists in Gen 5 is the O3 pipeline viewer. I don't know if all of you are or know it, What you can see here, the script size is a bit more maybe, but it shows the stages an instruction goes through. There's the fetch, decode, rename, dispatch, issue, complete, and retire. I tried to color the letters of the abbreviations accordingly. And you can also see the PCs, the macro operations, the sequence number. The dots means that the instruction will commit eventually, and the equal sign means it will be squashed. And yeah, this is like the motivation that led to us developing SecureView, because we want to gain this insight, and it can be used for debugging, but also for educational purposes. So to teach newcomers to the security field how such an attack may look like from a more microarchitecture point of view. And to this end, we augmented the Gem5 pipeline viewer with test-related information about which instructions potentially open a transient window, and also about which instructions are blocked. And yes, speculation can have different forms. There's control flow speculation. Also, there can be older instructions that may still cause an exception, memory dependencies, and memory ordering. And this is a common property used by almost all hardware mitigations. And there's the concept of speculative shadows, which means that unresolved speculation casts a shadow on younger instructions in the ROB. And in SecureView, we want to mark these instructions as shadow casting and then regularly check if they resolve. And then it looks like this. But let me zoom in a bit. Yeah, the O3 pipeline viewer was already kind of clustered, so we didn't want to add more information in the same line. So we created a new line for the security information. And then the example shows that the branch is unresolved, so it's casting shadow. And when it completes, the shadow is resolved. And during this time, the instructions, the younger ones, are considered unsecure. And yeah, let me walk you through some example mitigations. There is eager delay, speculative taint tracking, which we heard about earlier. And then there's also copy, which is the mitigation that we developed. And in eager delay, it's pretty simple and one of the first hardware mitigations. It just simply delays all speculative load instructions that could access the secret. And yeah, in our SecureView, we mark these as unsecure when they get inserted in the RB, and if there's an older shadowing instruction. And then we need to visualize the blocking and potential rescheduling when they are no longer shadowed. And this looks like this. So we have the jump instruction from earlier. We see it's casting a shadow here, and the this micro operation is a load. And then we see that it is blocked down here, and then rescheduled later when the other instructions become safe. SCT works by having a taint infrastructure, and a speculative access or load instruction initiates the taint bit, and the taint is propagated through the registers, and once the so-called transmitter instruction wants to be executed speculatively, it is blocked, and the taint is resolved when the youngest root of the taint becomes non-speculative. In SecureView, it looks like this. So we have, I cropped it a bit so to make it a bit readable, but yeah, here we see the first load. It initializes the taint here. And then we have the load down here, which is blocked. And we also have the youngest root of taint, which is the sequence number of the first load. And then we can see the propagation of the taint. So it is corrected, it is blocked. Our own mitigation works it delays less instructions than eager delay. and has a bit less hardware implications than SCT. And it works by loads that load from a data page. They enable a safe access bit. And then speculative loads targeting page that has this bit set, they are allowed through because can be assumed for sandboxing that the pages belong to the currently executing software. And speculative loads targeting different pages, they are blocked, so to prevent the piece of software from breaking out of its access rights. And yeah, I didn't bring a picture for this one because it looks similar to eager delay, but it has less blocked loads. And then in this picture, we can see an example attack. So it's the attack from the beginning of the presentation. This one is the branch condition, and here we have a load. And without any protection, we can see that the load is issued and completed. And this means that it accessed the memory location that we didn't want to access, and can lead to an attack. And yeah, here we can see that it's the same piece of software, and the branch instruction, it casts a really long shadow, and then the subsequent access instruction is blocked here. So yeah. As a conclusion, we have a simple tool, so it's just an extension to the O3 PipeView Python script that is able to visualize core aspects of mitigations. And it also helps analyzing the details of an attack. And for future work, yeah, we could display more detail of the intermediate chain tracking steps. And also for our own mitigation, it would be nice to have some way of visualizing what goes on in the memory subsystem, because currently there's no visual cue for why certain shadowed load instructions go through and certain don't. And it would be nice to have. These are the papers mentioned in the presentation, and thank you.
Thank you, speaker. Any questions?
Thank you. Cool. Are you aware of Konata tool? It's a visualizer someone has written, which is a graphical user interface program.
Okay, the question was if I'm aware of Konata, and I'm not. No, sorry.
Okay, maybe you should look it up. It's pretty cool. It basically uses the same output as the pipe view. And yeah, my question would be if you would consider adding this to Konata also, but if you're not aware, then I guess you don't have any plans.
Yeah, we don't have any plans yet, but might look it up after the presentation and see what can be done there.
Okay, and I have also a small question. How difficult was it to extend pipe view? Because I'm considering doing something similar.
The question was about the difficulty of extending pipe view. It was fairly straightforward, so it's simple Python code, and it was a bit of like trial and error, but it was okay.
Okay, cool. Thank you.
Thanks very much for the presentation, Joseph Rogers, NTNU. So if I'm a security researcher, when would you say that it makes sense for me to use a tool like this at the Gem 5 level as opposed to just working at the RTL level? Can you say some words about some of the things I should be thinking about in terms of which situations make sense to do it at either one?
Yes, thank you for the question. It was about when it makes sense to use such a tool compared to direct analysis on the RTL. And I would say, as it is for using Gem 5 versus RTL, it can be used for exploration and like a first idea if it works. But if you want to be really sure, you should resort to formal verification of the security, which can only be done at the RTL, which we also do in our group. So if you're interested in that, you can also pinpoint you to some papers.
Okay, no other, if there's no other questions then, let me check online again. No other ones, so let's thank the speaker one more time.